So for this problem, this is one of those at least kind of problems. So this says the test is 99.8% effective in saying it's negative if it's truly negative. If you don't have the antibody present, and it's saying you don't. So, and we're testing how many people here? 6 people. So we're assuming that each person's results is independent of the last one. So for part A, you're just going to take that probability and raise it to the 6th power, and that is, let's see, if we go to 4 decimal places, 0.9645. Now for part B, this is one of the buzzword here is at least one of the 6 people get a false positive. So here's the probability that nobody gets a false positive. So that at least probability you're going to remember is 1 minus none. Well, here's the probability of none, so we just subtract those, and that'll be the probability of at least one of them will get a false positive. Pretty small chance, really. So for this one, similar kind of thing. These are multiplication, these are and kind of probabilities because we're looking at both computers, so this and that. So let's see, for any one computer, the probability of this ancient is 0.84, and since we're looking at 2 of them, we just raise that to the 2nd power. Now they're saying for 9, well, it's the same deal. All 9 are ancient, so we don't have to do any subtraction or anything, so to the 9th power. Now, what's the probability that at least one of the 9 is? So the probability that all of the 9 is 0.84. So the probability that one of them is not is 0.16, because 1 minus 0.84. That's the probability of it not being cutting edge or not ancient. And they're going to raise that to the 9th power. So 0.16 raised to the 9th. That's a very small probability. We're at 0.0000687. Okay, pretty small. So we're going to take that away from 1 because it's an at least. So 1 minus that. So I'm getting 0.99999 yada yada yada. So it's almost a given fact. You could almost say it's guaranteed that at least one of 9 computers won't be classified as ancient if 84% of them are, based on those results. So would it be unusual for at least one of the 9 to be cutting edge? Most certainly not. It's almost guaranteed, right? So for this one now, we'll get 52 cards in a deck, and what you got to remember is there's 13 of each suit in the deck, and then there's 4 face cards, 4 tens, and all that. I'm assuming you know that. So what's going to compute the probability of drawing a diamond or a heart? So because we're using that or thing, what you got to remember is the probability of event A or event B with the upside down U is found by the probability of A plus the probability of B minus the probability of both A and B. Okay, that's a general addition rule. So a card can't be both a diamond and a heart. So for this first one, that's 0. So the probability of one card being drawn is 1 out of 52, and that'd be, diamond. Diamond would be 13 out of 52, plus 13 out of 52 for the heart. And we're going to add those 2 probabilities, so that's 26 over 52, and if we make that a fraction, I believe that's 1/2. Okay, so that's the answer for A. What's the probability of a diamond or a heart or a club? Well, let's see. Again, those are mutually exclusive events. They can't happen at the same time. So 13 out of 52 for the diamond, 13 out of 52 for the heart, plus 13 out of 52 for the club, which I believe is 3/4 if we do the reducing, so 0.75. So part C, compute the probability of a 10 or a club. Well, let's see. I know there's 13 clubs out of 52. Why did I write 53? Guess I can't delete that. There, let's try that again. So for a club, there's 13 out of 52. For a 10, there's 4 out of 52. However, there is 110 that's a club. So we don't want to count that twice. So if we're subtracting that, so that would be 13 plus 3 is 16 out of 52, and we can either make that a decimal, or what does that reduce? 4 out of 13. So now we've got 30 similar kind of problem. What's the probability that 2 random selected tulip bulbs are both red? Well, let's see. There are 14 tulip bulbs to start with, so for the first draw, there's 14 out of 32. Now, because of this, we're taking 2, unlike that last problem, here we're trying to say if they're this and that, not this or that. So for the first bulb, it's 13 out of 42, or 14 out of 32. But we've taken a bulb out, so now there's only 31 bulbs left in the bag, and there's only 13 red ones left. So we're going to multiply 14 times 13, whatever that is, and divide that by whatever 32 times 31 is. Okay, so what's the probability that the first bulb is red and the second is yellow? So that was A. For B, let's see, so we're going to have 14 red bulbs out of 32. And then the second bulb, there's 8 yellows, but there's only 31 left in the bag. So 14 times 8 divided by 32 times 31. So for part C here, the first bulb is, there's 8 out of 32, and then there's 14 reds out of 31. And if you think about this, this is the exact same answer as the last question. We're just changing the order, because it's still going to be 8 times 14 divided by 32 times 31. So that's kind of a cool little trick that sometimes you pick up on, sometimes you don't. So then for the very last one, what's the probability that one is red and the other is yellow? Well, see, they aren't telling us an order here, so we're going to do, consider the first bulb, if it's 14 out of 32, and then the second one would be 8 out of 31, but then we got to add in, because it's this possibility where it's a red, then a yellow, or we can do yellow, then a red. So it's going to be 8 out of 32 times 14 out of 31, or in other words, we're just going to get 2 of these. You could multiply the first answer times 2, or you can calculate this out. In addition to these notes that I've given you here on these 4 slides, I also want you to see, I want to see that you've done these 2 exercises out of the textbook, and I want to see those video notes you've completed. That, and you should take a look at the chapter homework, or the homework that was on Math Excel for this. Maybe print out what you've done and use that also. Okay? Once you get this done and you show it to me, I'll give you the password.